Welcome back, everybody. We're going to finish 7.2 today, Tuesday, April 7th. In this section, we are going to focus on multiplying and dividing rational expressions. And the key is, in order to be able to do so successfully, we have to always make sure that we completely factor all numerators and denominators. And unless you completely factor all of your polynomial numerator denominators, there is no hope in our ability to multiply and divide rational expressions. And so, ladies and gentlemen, again, we're going to have to revisit our Chapter 6 factoring skills that we've learned. What might be helpful in Chapter 7 is if you just bring the factoring toolbox and have it next to you, as you are going to be challenged with factoring all types of polynomials and being successful in this section. All right, so let's just dive right in. Let's look at how to multiply some rational expressions together. We'll look at this one, x minus 1 over x plus 1. We're going to take that rational expression and multiply it by this rational expression, 5 over x minus 1. The first step is we need to make sure that all of our numerators and denominators are completely factored. And with inspection, we realize that we cannot further factor x minus 1. X plus 1 is also completely factored, so is 5, and so is x minus 1. Being the case, ladies and gentlemen, since everything is completely factored, we are now able to perform what is called cross-canceling in much the same way we did when we had fractions that just had numbers in them. So notice that this numerator x minus 1 will cross-cancel out with this denominator of x minus 1. That's legal cross-canceling here. Since these rational expressions are separated by multiplication, we can do that. So therefore, we say x minus 1 divides into itself once, divides into this x minus 1 down here once. Notice there's no cross-canceling available between the 5 and the x plus 1. And so our final answer is going to be 1 times 5, or 5. And that sits over x plus 1 times 1, or x plus 1. And we're done. This is the correct reduced product of these two rational expressions. All right, let's try another one here. All right, so we'll take 8 over a squared minus 25. And we're going to try to multiply this by a minus 5 over 6 times a plus 2. All right, we're going to try to multiply these rational expressions together. And in order to be able to do that, first of all, we have to make sure that all of our numerators and denominators are completely factored. Notice 8, you could factor 8 down into 2 times 4, or even a 2 times 2 times 2, but we don't need to do that with numbers. A squared minus 25 can be factored. Upon inspection and thought, we realize that we have what's called a difference between two squares, and so a squared minus 25 will factor into a minus 5 times a plus 5 times a minus 5 cannot be further factored down, so we just bring it along. 6 is just a number, just bring it along, and the a plus 2 is completely factored. There's nothing we can do to further factor it, just bring it along. All right, so here we go. Now we're going to ask ourselves, can we do any cross-canceling between any numerators or denominators here? Notice between the 8 and the 6, we can do a little cross-canceling here. 2 divides into 6 3 times. 2 divides into 8 4 times. There's cross-canceling available this way between the a minus 5s. The a minus 5s drop out to 1s. And what are we left with? We're left with a numerator 4 times 1, or 4, and that will sit over 8 plus 5 times 3 times a plus 2, or 3 times a plus 5 times a plus 2. And notice there is no further reducing we can do between the numerator and denominator, as that's the last thing you should check. And this is it. This is your final answer for that problem. So we have successfully multiplied those two rational expressions together. Okay. This next one here is going to illustrate something interesting that does oftentimes occurs. We want to try to multiply these rational expressions together. But before we do so, we want to try to ask ourselves, can we do any cross-canceling? Well, before we can do any cross-canceling, of course, we've got to make sure that all our numerators and denominators are completely factored. X minus a cannot be factored down any further. A minus x cannot be factored. 3 and 12 are just numbers, nothing going on between those things there. Now something interesting occurs here. Notice that x minus a and a minus x are very similar looking. They look the same, but they're not exactly the same as is. Notice we have both these binomials have x and an a, but the negative sign's in a different place between these two different binomials here. Here the minus sign's in front of the a, and here it's in front of the x. Ladies and gentlemen, remember I indicated in the past that you can always factor a 1 or a negative 1 out of any polynomial. For instance, if you have, maybe say we have a polynomial 3x minus 2. If I factor a negative 1 out of a polynomial, what effect does it have on the polynomial? Well, if I factor a negative 1 out of both these terms, the effect factoring a negative 1 out of a polynomial has on the terms of a polynomial is to basically just toggle the signs of the terms of the polynomial. So a positive 3x then would become a negative 3x, and a minus 2 would become a plus 2. So you can see that when you factor a negative 1 out of a polynomial, the only effect it has on a polynomial is that it changes the signs of the terms. This is a time and a place where you'd want to factor a negative 1 out of either one of these binomials, and in doing so you'll discover that what you'll leave behind will be identical binomials. So here's what I'm going to do here. I'm going to choose the numerator here, and I could just as well have chosen this denominator down here, but I'm going to choose this numerator here, this x minus a, and I'm going to factor a negative 1 out of both these terms here, which is perfectly legal to do. So let's do that. Let's factor a negative 1 out. There it is. What would we leave behind in doing so? Well, when you factor a negative 1 out of a positive x, you'll leave behind the negative x. When you factor a negative 1 out of a negative a, you'll leave behind a positive a. I'm going to rewrite this down here because that's got it bunched up there. So we factored a negative 1 out of x minus a, and we leave behind this. Now, the importance of having factored a negative 1 out of x minus a is we should realize that negative x plus a is really the same as a minus x. These are identical binomials now. If you don't believe me, let's just spin these terms around here. Let's spin these terms around, in which case we'll really have a minus x. And now we can realize, ladies and gentlemen, that these binomials are identical, a minus x, and therefore they would cross-cancel out. So this a minus x would cross-cancel out with this a minus x, leaving behind factors of 1. What we would be, and notice we can also do cross-canceling here between the 3 and the 12. 3 divides into itself once, divides into 12 4 times. What we would be left with then, in the numerator, is just negative 1 times 4, or negative 4. and that would sit over 1 times 1 or 1. So this would reduce down to negative 4. So there might be a time and place whereby if binomials look the same or similar, by factoring a negative 1 out of one of your binomials, you can make it look like the other one. And that might lead to reduction, as we found out that it does lead to reduction right here. So in general, whenever you have a binomial like a minus b in general is always equal to negative 1 times negative a plus b, or is always equal to negative 1 times b minus a. That's always true. So in general, ladies and gentlemen, if you have a rational expression a minus b over b minus a, this will always reduce down to negative 1. Always. And again, here's why. If I factor negative 1 out of the numerator, I'll leave behind negative a plus b, which is negative 1 times, if I spin these two terms around, b minus a over b minus a. These b minus a's now reduce out, and we're left with negative 1. So in general, this is something worthwhile to remember. If you ever have the quotient of two binomials that differ only by where the negative sign is, they always reduce down to negative 1. Okay, let's try to divide some rational expressions. How do we do that? Well, in general, we have to go back to basic math and recall something. Recall in general that if you're dividing two fractions, do you remember what you need to do? Well, what you need to do is change your division to multiplication, but in doing so, you would flip your second fraction upside down, or in other words, take its reciprocal. So this is something you need to remember when you're dividing rational expressions, is you have to change division to multiplication and multiply by the reciprocal. All right, so let's try one out here. The instructions go from multiply to divide. 8 over a squared minus 25 divided by 16 over a plus 5. We change division to multiplication. Do not change your first fraction. Just bring it on along. Change division to multiplication. And now the second fraction has to be reciprocated. So we flip it upside down. So it's a plus 5 over 16. Now we're back to multiplying rational expressions. So in order to do so successfully, we have to make sure all of our polynomials are completely factored. 8 being a number, we just leave as 8. But a squared minus 25 is the difference between two squares, so it factors into a minus 5 times a plus 5. A plus 5 cannot be further factored down. Just bring it along. And 16 is just a number. We just bring it along here. Now we try to do any sort of legal cross-canceling here. Notice between the denominator of the first and the numerator of the second fraction, the a plus 5s drop out, so we can cancel out the a plus 5s. 8 and 16 cross cancel. 8 divides into itself one time. 8 divides into 16 two times. In the numerator, we're left with 1 times 1 or 1. In the denominator, we're left with 2 times a minus 5. And that is your final answer, or your final quotient, of having divided these two rational expressions. All right, try another one. Divide. Y squared minus 7y over 3y squared minus 48. We're going to try to divide that rational expression by this one. Again, to divide, first of all, we have to change division to multiplication and flip the second fraction upside down. So let's do that first before we forget. And now we're back to, can we multiply rational expressions together? Well, to do so, we have to make sure all of our polynomials are completely factored. Let's look at the numerator of the first fraction, y squared minus 7y. We should realize that we can factor a y out of both the first two terms, so we do so. And when we factor y out, we leave behind y minus 7. 3y squared minus 48. Now, I realize that 3y squared minus 48 may require more than one step to completely factor it, as I can first of all pull out a 3 out of both the first two terms, leaving behind y squared minus 16. Then I need to realize that y squared minus 16, being a difference between squares itself, can be further factored down. So y squared minus 16 is the difference of squares of y and 4. So we can factor down into y minus 4 times y plus 4. That is the complete factorization of 3y squared minus 48. Bring this complete factorization back up to the main problem and replace the denominator with it. Notice the numerator of the second fraction is a trinomial, one which is an easy type, leading coefficient being 1. To factor these types, all we need are two factors of the constant term that add up or sum up to the middle coefficient. So we're searching for a couple of factors of positive 12 that add up to negative 7. After a little thought, we should realize that negative 3 and negative 4 are the only factors of positive 12 that do indeed sum up to negative 7. Being the case, this trinomial immediately factors into y minus 3 times y minus 4. Y squared minus 9 is the difference between two squares, so this binomial can be factored into the product of conjugate binomial factors, namely y plus 3 multiplied by y minus 3. Now that all of our polynomials are completely factored, ladies and gentlemen, it's legal now to do some cross-canceling or reducing. And let's see, what can cross-cancel out this way? Nothing. How about this way? Anything? Well, the y minus 4's drop out. Can we do any reducing between the top and the bottom? Well, notice this y minus 3 here reduces out with this y minus 3. That's legal. And so what are we left with in our numerator? We're left with y times y minus 7 times a bunch of 1s. So we're left with y times y minus 7. And that's all going to sit over in our denominator, which just has 3 times y plus 4 times y plus 3 left. And this is it. We are done. We cannot reduce this any further. This would be our final quotient for having divided these rational expressions back up here. To divide these rational expressions, again, you have to, first of all, make sure you change division to multiplication and flip your second fraction upside down. Now, this seems kind of tedious to have to rewrite this like this, but you got to remember to do it. That should be a minus 7y squared plus 10y. And you guessed it, ladies and gentlemen, now we have to completely factor all of our polynomials. So if nothing else, we're getting a huge workout from Chapter 6 and our ability to factor polynomials. And you can see why Chapter 6 precedes Chapter 7. If we don't know how to factor polynomials, we're not going to have any success in Chapter 7. All right, how can we factor y squared minus 5y? Well, we can factor a y out of both these terms. Let's do that. That numerator has been completely factored. Now let's look at the denominator. Notice we have a trinomial. Nothing we can factor out of all three terms except 1 or negative 1. And so therefore we try to factor this as an easy type of trinomial where we need two factors of positive 12 that sum up to the middle coefficient of positive 7. And the only factors that work are going to be a positive 3 and a positive 4. Hence, this denominator trinomial factors immediately into the two binomials of y plus 3 multiplied by y plus 4. That's completely factored. Now we shift our attention to the numerator of the second rational expression. Notice again, it's an easy type of trinomial, one with a leading coefficient of 1. We need two factors of 18 that do sum up or add up to the middle coefficient of positive 9. The only factors of positive 18 that will work are going to be 3 and 6. 3 times 6 is 18, and 3 plus 6 add up to 9. So this numerator trinomial factors immediately in the two binomials of y plus 3 multiplied by y plus 6. That trinomial has been completely factored. Now we got one more down in the denominator. Notice this one, we can factor something out of all three terms, namely a y. We need to pull a y out first. And when you pull a y out first, you leave behind y squared minus 7y plus 10. Now here's the kicker, ladies and gentlemen. Notice this trinomial inside the parentheses that we leave behind after factoring y out of all three of these terms itself can be further factored down. But you know what? I should have taken this whole denominator off the side of my paper and factored it completely, but because I failed to do so, now in factoring this remaining factor of y squared minus 7y plus 10, I'm going to have to rewrite this problem all over again and just show that I factored just this factor here. So again, sometimes it might be wise to take the whole polynomial off to the side of your paper and completely factor it first, and then bring back its completely factored form back to your main problem. But at any rate, since I have my situation as is, I'm going to have to deal with it. I need two factors of positive 10 that sum up to negative 7. And after some thought, negative 2 and negative 5 are the only factors of positive 10 that do indeed add up to negative 7. So here we go. Now we're going to have to rewrite our problem all over again here. Now, this trinomial factors into y minus 2 times y minus 5. And that's completely factored. Now that all your polynomials are completely factored, it's time to ask yourselves, can we do any cross-canceling or reducing? Notice this y here will reduce out with this y down here. Y minus 5 will cross-cancel out with this y minus 5 down here. Y plus 3's will cross-cancel out this way. And that's about it. So what do we have left in our numerator? Just a bunch of factors of 1. And we got a y plus 6 that survives up on top. In our denominator, we have a bunch of factors of 1, and we have a y plus 4 and a y minus 2 that remain. Now, you do not have to multiply these binomials back out. It's a waste of time. Ladies and gentlemen, we are done. This is your final answer. This is your final quotient of having divided these two rational expressions. So you can see the moral of the story is here, we have to completely factor all of our polynomials before we can have any chance at doing any cross-canceling or reducing. You cannot start doing voodoo math, ladies and gentlemen. You can't just start, canceling out the y squareds here, the y squareds here, the y's. You can't do that because separating these terms are additions and subtractions. You have to completely factor all your polynomials first, chapter 6. And then, and only after doing that, can you then do legal cross-canceling or reducing. So I will give you practice in this section. The key is practice. I mean, we have got to take it upon ourselves to spend some time with this material, ladies and gentlemen, and go through a lot of practice problems. That's the only way we're going to, become proficient with this material. So please do spend time in practicing a lot of these. The more practice you give yourself, the more confident you're going to become, the more accurate you're going to become, and your efficiency is just going to increase also. So I wish you the best of luck. Please don't give up. We're almost done with the semester. If you ever have any questions, please let me know as soon as possible. Thank you. Stay healthy. Stay safe.